All right, this video is going to go through and introduce the next section, 8.8. The topic of 8.8 is called improper integrals. So I am not going to do examples in this video. Instead, I just want to kind of take you through what makes an integral improper and how we deal with it. And then I will make a separate video that actually goes through and does the examples. So this is more of a informational introduction type lesson here. So there are two ways that an integral can be something that's improper. To this point, any integral you've ever been asked to do has not been improper. We're really going to focus with this on definite integrals. Definite integrals are integrals that have boundary numbers. So we have done definite integrals since about halfway through Calc 1. And to this point, they were all ones that could be done either by hand or ones that could be done on a calculator using a math button and the math 9 to evaluate a definite integral. These are not ones that can be done on the calculator. So let me show you what's happening here. The first way that an integral can be improper is if you have a definite integral where one of the boundaries or both of the boundaries are infinite. So what you'll notice with this is something like this, where these are very obvious to see. You'll see an infinity as the upper bound. You'll see a negative infinity as the lower bound, or the worst case scenario, worst case because it's the most amount of work, both of your boundaries are infinite, your lower boundary being negative infinity and your upper boundary being infinity. For these first two, for this one and this one, your lower boundary and your upper boundary can be any constant. So you might have an integral that goes from like 5 to infinity. That would be an improper integral. Or you might have an integral that goes from negative infinity to 7 or something like that. Again, an example of an improper integral. The second way that an integral is improper is more subtle. I think the ones that you see an infinity sign on your integral symbol, it's going to be pretty obvious that this is not your run-of-the-mill integral. This second type, though, you might have to do a little more detailed look at it to see if there's an issue with it. And this is going to happen when either your boundaries create a discontinuity in what you're trying to integrate, or somewhere between your boundaries there is a discontinuity. So we're looking for what's called a finite number of discontinuities within the limits of integration. So if you look at this first one, the reason that this is improper is because this function, 1 over x, has a discontinuity at x equals 0. And if you look at your boundaries go from -2 to +2. 0 is contained between those boundaries. So essentially what you have is you have an asymptote right in the middle of your interval. It doesn't have to be in the smack middle. It can be closer to one boundary than the next. But if you have that discontinuity, we call this an improper integral. If you would try to do an integral like this on your calculator, so you go to math 9 and you would type it in, it would give you an error. I can't remember exactly what the calculator says, but it has something. I think it says something about something about the boundary issue. Another example would be one where the actual boundary numbers themselves are the problem. So this is one where you have a lower boundary of 3, you have an upper boundary of 7, and those actually happen to be the two places where this function is undefined. So again, having a discontinuity either on a boundary, lower or upper, both, or having a discontinuity between the boundaries creates what we call an improper integral. So I've even seen questions on AP tests that ask that, is it improper, or explain why it's improper. And those are the things you're looking for. You're looking for either an infinite boundary, top, bottom, or both, or you're looking for a boundary that has a discontinuity or either on the boundary or between the boundaries. So here's how we fix it. The way that we fix improper integrals is with limits, which is why we spend that time talking about L'Hopital and limits. It seems very out of place in this chapter until you realize this last section of the chapter kind of combines those two things. So if you have the first improper integral is when you have an infinite upper boundary, the way that we fix it is we can't actually plug infinity in because it's more of an idea or a concept, but we can look at what happens as we approach infinity, and that's what limits do. So what you'll notice is this improper integral is rewritten as the limit as we go to infinity, and you can use any letter you want. Out of habit, I tend to use b if it's the upper boundary that's the issue, because we tend to call b that generic upper boundary. So we're going to evaluate the limit, but when we think about what happens when I put these boundaries in, we're going to take b going to infinity. What happens as that boundary gets bigger and bigger and bigger? If the issue is the lower boundary, so if you have a situation where your lower boundary is what causes it to be improper, same type of fix. We rewrite the integral as a limit as we approach negative infinity. Again, I use the letter a just because usually our lower boundary is generically called a. You could write anything you want. don't make it x because we're already using x in my function notation. So a's and b's are good things to stick with. So the way that we fix it is we take the limit as a or whatever letter you chose goes to negative infinity, and then rewrite your definite integral and just being very generically and putting an a. So you might have something like this. It may say, I want to integrate, get rid of that. I want to integrate from 5 to infinity of 1 over x. And then your fix would be, I'm going to take the limit as b goes to infinity and write it as the integral of 5 to b. So that's how we're going to rewrite these improper integrals in a limit notation. It is so easy to not write the limit, to just kind of do it without writing it. I have seen on AP tests in their rubric, if you don't write the correct limit notation, if you don't show how to fix it and use a limit, the limit notation, they won't give you full credit. Now, on the flip side, if you can't remember how to integrate it or you struggle to go from here, just doing what I just wrote down, just writing a limit notation to fix it, is good enough to usually earn at least a point. Sorry, one more. So here's the one that I said was my least favorite with the infinite limits. It's what do you do when both bottom boundary and top boundary are infinity? The only way to fix that is actually to break it into two integrals. We've talked about integrals being like part plus part equals whole. So somewhere between negative infinity and positive infinity, we have to stop and set up a new integral. The easiest way to do this is to have 0 kind of be that stopping and starting point. You could use any letter. You could go from A to 1 and 1 to B, but we try to work with numbers that are easy. 0 is very easy. 1 wouldn't be awful either. So this is the way that we fix it. We set up an integral to fix the lower boundary. So we're going to talk about what happens as my lower boundary goes to negative infinity, and then stop it at, again, 0 of the function. And then the second part fixes the upper boundary and look at a limit as we go towards positive infinity. The reason that I say this is my least favorite type is that one's way more time consuming. The good part is I've seen a lot of improper integrals show up in the AP test, and it is very uncommon for them to pick this one for you to do. The most common one that's been on AP tests is having an upper boundary that's infinity. Of all the different improper integrals I've seen over the last decade, that seems to be the one they ask about the most. I'll do the most examples with it too. So when we get an answer for these, we have different types of answers. We have different descriptions. If we go through this process and we evaluate this improper integral and we take the limit and we actually get a number, so we get something like 5 or a half or -3, we say that my improper integral is a converging improper integral. What that means is it's converging on that number. It's getting closer and closer to that value. The visual representation, so let's say this integral was going from 0 to infinity, and I wanted to evaluate that limit or that integral as we go to infinity. What this is basically saying is the area under a curve, because that's what a definite integral represents, is getting closer and closer to a finite value. So if you go through this full process and your final answer ends up being 5, we would say that the area under the curve is getting closer and closer to 5. We call that a converging improper integral. Some of your problems will ask you that to tell you to describe what type of improper integrals. When they ask the type, they're asking, is it a converging, or the second option is it a diverging improper integral? A diverging improper integral means that your answer, your limit, is getting really, really big, going to infinity, or it can even be getting really, really small, going to negative infinity. Here's what this means. This means that if I evaluate my limit, so let's say this is my function, some curve here, and I want to know what happens as I integrate from a to infinity this function. Notice that the area under the curve just keeps getting larger and larger and larger as I go out. I can kind of shade it in and say, here's my area. It's not converging on a value. It's not looking like it's eventually going to kind of close off, even though technically that never fully closes off. This one's just getting huge. That's why we call this a diverging improper integral, because that answer is not converging on a value. It's just getting really, really big. You can get a negative infinity, and what that's basically saying is that my answer is underneath the axis. The x-axis, if you think about definite integrals, the sign of the answer talked a lot about where the area was located. So as you go through and do problems, one of the things that will be asked is, tell me about the type. Is it converging, meaning you actually get a finite number, any number, positive or negative, even 0, or is it diverging, meaning you get an infinite answer? So your second type of improper integral is the one that was the more subtle one. First type is the one that has infinity or negative infinity as a boundary. The second one is, what do you do when it's a number that's a discontinuity, either the boundary number or between that? So we have three options here. Either the lower boundary is the problem, the upper boundary is the problem, or somewhere between the boundaries is the problem. And when I say the problem, I mean the place where we have a discontinuity. So here's how we deal with the first. What do we do if the upper boundary is the problem? So that's what this one. This is an upper bound issue. I like having an example here so you can see kind of a very straightforward one and not see one that's written really generic. So here's the problem with this one. Your upper boundary, 1, makes this function undefined. That's a place where we have a discontinuity or an asymptote. So we need to fix that. So the way we fix it is still with limits, but now we're fixing it with one-sided limits. One-sided limits were the limits that either we're approaching it from the left side or the right side. So if we approach a limit from a number to the right, that's what that plus sign means, or a number from the left, that's what the minus sign means. Doesn't need a 1 there, just a minus sign. So the fix is, I'm going to use this hard and fast example to help me here. I can't put 1 in, so I can start integrating from 0, my lower boundary, and I can go all the way up until we get to 1. But I can't get all the way to 1 because if I plug 1 in, it's undefined. So we use what's called a left-sided limit or a left-handed limit to say I want to get really close to 1 from the left side and then stop. So my fix here is I would say I'm going from 0 to, and you can use any letter you want. C is one of my favorite letters. You could even use B because that's our upper boundary. We're going to have that boundary get really close to 1 from the left side and then evaluate the limit. So that's kind of our fix for that. If the upper boundary is the problem and it's a number, a finite number, we want to approach it from the left. Same idea if it's the lower boundary that's the problem. And again, having an example that's more concrete really helps the understanding. For this particular one, x can't be 0. Because if I put 0 into that function, I get something that's undefined. That's where the asymptote is. So I can't put 0 in, but I have to go from something right after 0 all the way until we get to 2. 2 is my upper boundary, and that's not a problem. So the way I fix it is I fix it with a one-sided limit that's from the right. So I'm going to say, well, I can't start at 0, but I can start just past 0, which is what a limit as we approach 0 from the right means, and then I can go to 2. So again, I fix it by rewriting it as a limit notation of a definite integral, being kind of generic. And again, you can use any letter you want for this. I often use A if it's the bottom boundary that's the issue, and B if it's the upper boundary. And then the last option is, what happens when the discontinuity isn't the lower or upper boundary, but it's a number in between? This is also the worst one to deal with, but thankfully the least common. If the discontinuity happens between the lower boundary and upper boundary, so looking at this example, 1 over x can't be 0 when I put my x values in. That's where my discontinuity is. And if you look at your boundaries, -1 and 3, they're okay, but 0 falls between -1 and 3. So in this interval, you have this discontinuity. What's going to happen if you try to do this one on your calculator? It's going to give you an error because it's having trouble figuring out what my area is because there's an asymptote in between the two boundaries. So the way we fix it is we fix it by breaking it up into 2 separate integrals with 2 separate limit fixes. So first I have to see what's happening before we get to 0. So that's what this first part is saying. Let's go from -1 until we get to 0 from the right. And again, use any letter you would like. And then let's pick up after 0. So a right-sided limit and go to 3. So we're kind of stopping and starting just before the problem number, which is in this case is 0, and then starting up right after that problem number. This one can be kind of a pain because, again, it's that multiple integrals and it just creates more steps for you to do. With both types, when you're done with these, you are still going to tell me if your final answer is converging because you get a number like 5 or 2 or 1/2 or 0, or diverging because when you're all done with your integrating and you're evaluating, you get an infinite answer. We're going to go through and do an example, some examples in another video, but this at least gives you some way to kind of have that foundation of what are we even dealing with when we start. So let me finish this, and you'll have another video to do examples.